Welcome everyone, and in this video I'm going to handle thermodynamics and kinetic stability of certain chemical reaction, and I'm going to do this in relation to entropy. Now, as we said earlier, that entropy is just the measure of disorder. Now, previously we went ahead and discussed about entropy of a system, we also went ahead and discussed about entropy under standard condition of the surrounding. Now, and lastly, we went ahead and discussed entropy total, meaning in any chemical reaction, now we are taking consideration the system and the surrounding of that given chemical species that were undergoing a reaction. Now, and from the analysis now, there are some summaries that I want to make. And the first summary that I'm going to make is based on the entropy total. And we went ahead and looked at it, that whenever we want to calculate total entropy, we are taking into consideration entropy of the system, and we are getting a summation of it and entropy under standard condition of the surrounding. Now, if you look at this, under what conditions were we getting a positive total entropy? Now, what you have to know and understand here is that total entropy can only be positive under certain conditions. It can only be positive under certain conditions, and the first one being if both entropy of the surrounding and entropy of the system are all positive. So when we have entropy of the surrounding and also the entropy of the system being positive, obviously total entropy will be a positive value. Second scenario, which can lead to a positive entropy, is when the entropy of the surrounding is positive and the entropy of the system is negative, and the entropy of the system is negative, but the magnitude or the degree of positivity, the magnitude of entropy of the surrounding is greater is greater than that of the system. So meaning I will only have a positive total entropy when entropy of the surrounding is greater than entropy under standard condition of the system. I will obviously get a positive total entropy for that given reaction. The third scenario, which can lead to a positive entropy, is when the surrounding is negative and the system is positive. It's positive, but the magnitude of the surrounding is less than the magnitude of the system. So meaning my delta S surrounding will be less than the magnitude of delta S of the system under standard conditions both. So those are the three major scenarios upon which we can have positive total entropy of a given reaction. Now, imagine a situation whereby we have an example reaction. And the reaction I'm going to have here is when methane is reacted with oxygen to yield carbon dioxide gas plus water. I'm not forgetting the state symbols. Now, this reaction, the first thing, the delta H of this reaction under standard condition is equal to negative 890.3 kilojoules per mole. Then the delta S under standard condition total of this reaction is equal to positive 2.95 kilojoules per mole. Now, there's something funny about this reaction. If you look at the delta H of that given reaction, the enthalpy change for this reaction is an exothermic reaction. What does that one tell us? It is a reaction upon which, when it is occurring, heat is lost. Heat is lost. And where is that heat going? The heat is absorbed by the surrounding. Another thing, this given reaction has a positive delta S total. And since it is having a positive delta S total, so we can qualify that this reaction is thermodynamically feasible. Is thermodynamically feasible. At room temperature. Meaning the reaction is feasible at 298 Kelvin. If you look at that reaction very well. But most of the time, you'll realize that the reaction cannot proceed unless it is ignited using a flame. And this is the main scenario we have with the cooking gases that we have at home, cooking cylinders. We always have propane and butane used. So in a scenario where I'm having C, sorry for that. In a situation whereby I'm having a C4, H10. So this is my butane. I can also have propane being used. This is a C3, H8. This is propane. Most our cooking cylinders at home contain these two gases. But imagine a situation whereby the gas is leaking. Unless it is ignited, a flame will never produce. A flame will never be produced. So that's the same scenario with methane here. So unless this reaction is ignited, oxygen will never mix with the methane and give us a reaction. So what are we supposed to do? Such a reaction needs to be ignited, and when it is ignited, we say the ignition is used to overcome the higher activation energy. So these two substances, both oxygen and methane, have a higher activation energy. So the ignition here is just to overcome the flame provided overcomes the high activation energy. Activation energy needed for the reaction to begin. Now, in a situation whereby certain reactions needs to be ignited for them to start reacting, such reactions are said to be kinetically stable. They are kinetically stable because unless they are ignited, they will never start reacting. So the ignition overcomes the higher activation energy that they have, is when now a reaction can start occurring. But immediately the reaction starts, the energy produced during that reaction is enough to sustain the reaction until it goes to completion. So such a reaction, for example, the one we have there, is kinetically stable because it can't ignite itself, but it is thermodynamically unstable because it is feasible. It is feasible at room temperature. It is feasible at room temperature. So those are the key things that you need to know. And this is a factor that is played by temperature. This is a factor that is played by temperature. In most substances, whenever they are reacting, there are those substances that have low energy. They'll need a lot of heat, and the change in entropy will be drastic. For example, if I'm having a cold substance, for example, ice, and a warm substance, a warm water here. So I can use warm water or the liquid water. It's a little bit warm. So you'll find that ice is 0 degrees. Maybe it is negative something. But maybe at room temperature, if water takes the temperature of the room is held in, we'll assume that it is 25 degrees Celsius. So if both two substances are supposed to be heated, you'll realize that ice will absorb more heat to get to vapor. But the liquid water we have at a temperature of 25 degrees Celsius will absorb less heat to get to vapor. So those are the key things that any chemist should have to know in relation to thermodynamicness and the kinetic stability of certain reactions. So a reaction might be thermodynamically unstable, but it is kinetically stable. And another reaction can be kinetically unstable, but thermodynamically stable. So thank you very much and have a wonderful